this video, we will be resolving vectors into components. So let's hop right into our first example. An 80-kilogram clown standing on a platform is strapped to a rocket that exerts a horizontal force of 2,000 newtons. What other force is acting on the clown that isn't specified? And it's going to be gravity. So that force due to gravity is going to be the mass of the clown times that acceleration due to gravity on Earth, which is 9.8, and we get 784 newtons in that downward direction. So let's determine the angle the clown makes with the horizontal as he travels through the air. So we have the horizontal force of 2,000 newtons that is being exerted. Here's the clown. We also have that downwards force of 784 newtons. Both of these forces are acting on the clown. So how is it actually moving through the air? Well, I'm just going to take this downward force and shimmy it right over here. And then I'll draw my resultant force. So that's going to be the actual motion of the clown. And the first question is, what's the angle with the horizontal? So we want this. And with that angle, my opposite is 784, 2,000 is adjacent, so I'm going to use tan because horizontal and vertical has a right angle, so that is loud. Tan theta equals 784 divided by 2,000. I'm going to take the tan inverse of this fraction, and I get approximately 21 degrees. Therefore, the clown makes an angle of 21 degrees with the horizontal. And what is the magnitude of the resultant force? So I'm going to use Pythagorean theorem here because I'm looking for the hypotenuse. So my resultant squared would equal the squares of the other two forces, but I'm just going to jump straight to the square root of the sum of the squares. And I get approximately 2,148.2 newtons. And I could have also done SOHCAHTOA to solve for the hypotenuse, but I wanted to use original information. So therefore, the magnitude of the resultant force is 2,148.2 newtons. Now, a vector can be resolved into two perpendicular vectors whose sum is the given vector. And that's exactly what we just saw in the previous example. We had this resultant force, but that resultant force is made up of these two perpendicular forces, the horizontal and the vertical one. Okay, and in most cases, those two components will be vertical and horizontal forces acting on the object. Now, in the clown example above, we can say that the resultant force of 2,148.2 newtons had a horizontal component of the 2,000 newtons and a vertical component of 784 newtons, so that gravitational pull. So let's try an example where we're given the resultant force and we need to figure out one of the components. Moaz is pulling his friend Amir on a toboggan with a rope that makes an angle of 25 degrees with the ground. If Moaz is pulling with a force of 70 newtons, what is the horizontal force being exerted on the toboggan? So I'm just going to say, here's the toboggan, and here's the ground, and he is pulling his friend so that the rope makes an angle of 25 degrees with the ground, and the force is 70 newtons. Now this force is the resultant force of the horizontal and the vertical components. So I'll call this the horizontal force and the vertical force. But we are just being asked to find the horizontal force. Oh, and I forgot, we have a right angle here. So I'm looking for my adjacent side, and I have my hypotenuse. So cos 25 degrees equals the magnitude of that horizontal force divided by the hypotenuse. Cross multiply, and then we can multiply these. Now you'll notice the calculations aren't anything fancy. So once you have your diagram, you're back to calculations you've done in the past. So therefore, a 63.4 Newton horizontal force is exerted on the toboggan. Now we have added 3 or more forces before, but sometimes it is easier to add 3 or more forces when you break each force down into its horizontal and vertical components. And then once you do that, to find your resultant force, you're just going to add all of the horizontal components and add all of the vertical components. So this is a really nice strategy when you have more forces, like 3 or more. If it's just 2, you can use your nice parallelogram law or triangle law, but when it's more than that, your diagram can get quite complicated. So using the horizontal and vertical components can be very nice and a little easier. So let's look at this diagram. So let's say this is one of your forces or one of your vectors, vector v, and I resolve it into its horizontal and vertical components. At this point, I would be making an assumption that I'm given the magnitude of the vector itself and I have the direction of that vector. So we know that the magnitude is the hypotenuse, the vertical component is opposite, and adjacent is the horizontal force. So when I'm looking for that horizontal component, I'm using cos of the angle equals the horizontal component magnitude over the magnitude of the vector itself. And then if I cross multiply, I end up with the following. So if I want to find the horizontal component of my vector, I can just multiply the magnitude of the vector by cos of its angle. And then I can do the same thing for the vertical component, but when I'm looking for the vertical component, I'm using the opposite side, which means I'm going to use sine instead of cos. But then it's the exact same thing. If I want my vertical component, I'll just multiply the magnitude of my vector with sine of its angle. And like I said, this can be really useful when you are adding 3 or more forces, because the resultant force can be calculated using these components. If I take all of my horizontal components of however many forces I have, I can add them all up, and that will give me the horizontal component of the resultant force. And exact same thing for the vertical component. I can find all of the vertical components, add them up, and that will give me the vertical component of the resultant vector. Now, how does that help us? Once you find your horizontal and vertical components, well, your magnitude is going to come from Pythagorean theorem. The resultant magnitude squared is going to be the horizontal component squared plus the vertical component squared of those sums, the sum of all the horizontal, the sum of all the verticals. You get your resultant horizontal and vertical components, then you're doing a Pythagorean theorem. So how can we find that resultant vector? We just take the square root of the sum of the squares. And direction, again, just using some SOHCAHTOA knowledge. If I have the vertical component, which is opposite to my angle, and I have the horizontal component, which is adjacent to my angle, then I can use tan. Tan theta is the vertical component divided by the horizontal component of the resultant. So let's give this a try. I have three vectors here, all acting on an object that is, let's say, right at the origin. I'm going to figure out the horizontal and vertical components of each of these forces instead of me trying to take each of the forces, lining them up head to tail to find this resultant vector, which might be a little messy because of the diagram, and it would take multiple calculations because I would have to find one resultant vector at a time. For example, let me add force 1 and force 2, then let me take that to add force 3. That way I can use the triangle law 2 times. And that can be tedious. You can make more mistakes along the way. So I'm going to organize my work here in a table. So this will be for my horizontal components. This will be for my vertical components. And I'm going to start with force 1. The first force here, okay, remember its components would look something like this, horizontal and vertical. Now, the actual angle of the force is not 75 degrees from the horizontal. Its angle is 180 minus 75, which is 105 degrees. And I need to take that into consideration when I find my horizontal and vertical components, because if you look at the position of this force, the horizontal one is going in a negative direction, whereas the vertical is going in a positive direction. So I would expect to see that. Now, if I did just use the 75 degrees in my calculations and did 50 sine 75, 50 cos 75, I would just have to pay attention to my diagram to make sure I take the direction into consideration later on, and that would be perfectly fine. But for my horizontal, the horizontal is adjacent to my angle, so that's going to be using cos. So the magnitude times cos of 105. And I get approximately negative 12.9. For vertical, I'm doing 50 times sine of that angle, and I get approximately 48.3. So 12.9 in that, let's say, west direction for horizontal, and 48.3 newtons in the upwards direction. Force 2. Well, this one, nothing crazy. Here's the horizontal, here's the vertical. I'm expecting 2 positive forces. The angle is given to me. It's exactly 30 degrees. So I'm going to do 70 cos 30 degrees. And notice I'm not doing SOHCAHTOA and cross multiplying every time. I'm just going straight to the cross multiplied version to save me time. And I get 60.6 newtons, positive direction, great. And then I'll do 70 times sine 30 for my vertical, and I get 35 newtons, positive again, fantastic. Now I can go to my third force. Now for my third force, here's my horizontal component that I expect to be positive, and negative for the vertical component. Now I can use the angle 42 degrees for both calculations, but when I do, I'll just make sure to add a negative for my vertical component because that's what my diagram is showing me. I can also find the angle itself. It's going to be 360 minus 42. So I can use 318. Either way, whichever angle you use, you should always do a little logic check afterwards to make sure your direction is good. So 60 times cos 318, and I get 44.6 newtons, and then 60 times sine 318, and I get approximately negative 40.1 newtons. Now I can finally find my resultant force. So for my horizontal component, I'm going to add negative 12.9, 60.6, and 44.6. And we get 92.3 newtons horizontally. And for the vertical, we add the 48.3, 35, negative 40.1, and we get 43.2 newtons. So these are both positive values. So if I were to do a little sketch, my horizontal one might be something like this. The vertical is a little smaller. Here is where the overall resultant force would be from the sum of all three of those forces. And now we need the magnitude of the resultant. So I'm going to take the square root using that Pythagorean theorem. So 92.3 squared plus 43.2 squared. And we do get approximately 101.9 newtons. Now for our angle, tan theta equals the vertical divided by the horizontal. And if we take a tan inverse of that, we should get approximately 25 degrees. So therefore, the resultant force is 101.9 newtons, 25 degrees above the horizontal. It didn't specify what kind of direction I should give, whether it should be quadrant, true, or this standard position, so I just gave it in this format. All right, some new notation. Now, when we resolve a vector into components and we're using these horizontal and vertical components, that should remind us of the x and y axis. So we can use vector I as a unit vector that follows the positive x-axis, and vector j is the unit vector in the direction of the positive y-axis. And notice you have that little hat on top of the I and j, giving us that information that it is a unit vector. So we can express our horizontal and vertical components using these unit vectors. For example, if vector v is the sum of 4 times vector I plus 3 times vector j, I'm going to draw myself a little diagram here. So here's the positive x-axis in this direction. Now, if I have 4 times this unit vector, the magnitude of this horizontal vector should be positive 4. And j is in the positive y-axis direction, but I have 3 times vector j, so 3 times a unit vector is just 3. So these are the horizontal and vertical components, and our actual vector is this right here. There's vector v, there are its horizontal and vertical components. Now I can find its magnitude and its direction. Well, for its magnitude, I'm just going to take the square root of the sum of the squares of the two sides. So that would be 16 plus 9, which is 25, and the square root of 25 is 5 units. For the angle, this is the angle I want. So tan theta equals 3 over 4, opposite over adjacent. And if I take a tan inverse, I get approximately 37 degrees. So there it is. So let's try a similar example as the one where we added 3 forces. But this time, we're going to draw our own diagram, and we might use the unit vectors a little bit. So find the resultant of 3 forces, and we're given the 3 forces. So I'm going to start with a diagram on the side here. Okay, force 1, 50 newtons at 60 degrees above the positive x-axis. Okay, so 60 newtons here, and that's 60 degrees. So this is going to be my horizontal, this is going to be my vertical component later on. My second force, 45 newtons at 20 degrees below the positive x-axis. 20 degrees, maybe something like this. And then we'll have the horizontal and the vertical component, and this time it's going to go downwards, and it's 45 newtons overall. And finally, we have force 3 is 30 newtons at 150 degrees above the positive x-axis. So 150 puts us in quadrant 2. So let's say like this, and it should be a bigger force. And our angle of 150 is this entire thing. And our components, our horizontal one is going in the negative direction. The vertical is going in the positive direction. So now we're ready to go. Write each force as a vector using the 2 unit vectors. Okay, well, if you want me to do that, you need to figure out your horizontal and vertical components first. So I'm going to create a little chart here. I'm going to write my horizontal component, my vertical, and then in that last column, I'll put that unit vector notation. So let's start with the first force. This one has a magnitude of 50. And for the horizontal force, it is adjacent to our angle. So I'm going to do 50 cos 60 degrees. And when I do that, I get actually exactly 25 newtons. For the vertical component, I'm going to do 50 sine 60. That's going to be positive as well. And it's approximately 43.3. So when I write that using those I and j unit vectors, horizontal is along the x-axis, so we're using vector I. So 25 times unit vector I plus 43.3 times unit vector j. And that's equivalent to force 1. So let's try force 2. So here, force 2, the angle is 20 degrees below the x-axis. I can use that, or I can use the outer angle. I can also use 360 minus 20, which is 340 degrees, which is what I'm going to do. This force was 45 newtons, so 45 cos 340. And I do expect a positive number here. I get 42.3 newtons. 45 sine 340 gives me approximately negative 15.4, which I was expecting because of that downward direction. So force 2 is equal to 42.3 times vector I minus 15.4 times vector j. All right, force 3. And I just noticed I labeled the force incorrectly. It is 30 newtons, not 150. So 30 times cos of the angle. And when we do that, I expect something negative, which we do get, negative 26.0 newtons. Then 30 sine 150, I expect something positive here. It's actually exactly 15. So force 3 is equal to negative 26 times vector I plus 15 times vector j. And now I can use these unit vectors as a way to communicate my resultant force. So for my resultant force, I can just add all 3 of these. 25 times vector I plus 43.3 times vector j. And I'll list out all of the components. And now I'll collect my like terms. 25i, 42.3i minus 26i. which should give me 41.3 times vector I, and then 43.3 minus 15.4 plus 15, 42.9 times vector J. So now I can see here's my horizontal component because I is along the x-axis, horizontal is parallel to the x-axis, and J is my vertical component. And now we're back to normal. I'm going to find the magnitude of my resultant vector with that Pythagorean theorem. And I get approximately 59.5 newtons. And now we can find the direction, vertical divided by horizontal, and our angle is approximately 46 degrees. And when you're doing the angle calculation, if you forget which way to divide your sides, just draw a diagram. Horizontal, vertical, here's the resultant, here's the angle. And then you can see here's my opposite, here's my adjacent. So in all the examples we've done so far, our components have been horizontal or vertical, but they don't have to be horizontal or vertical. They just have to be perpendicular to each other, and the resultant force has to be the given force. So when an object is resting on a ramp, we of course have the force that is going straight down, that is due to gravity. So this force right here is the force due to gravity in the downwards direction. And this force can be resolved into its rectangular components. So to create these components, we would have something like this. Okay, these two forces are perpendicular to each other. Now, these two forces are the normal force and the force of friction. The normal force is a force that is perpendicular to the ramp. So this here is perpendicular to our ramp, and it is pushing upwards against the box and works against the weight to keep the box at rest. So the key thing here is that it is perpendicular to the ramp and it is pushing upwards. So if I draw my arrow right here, there we are. There's the normal force. Then we also have the force of friction, and this one is parallel to the ramp. And here we are. Now, these three forces, the force of friction, the normal, and the force of gravity together, if you add them up, you should have the zero vector, because this box on the ramp, it's not moving. If it's not sliding down, it must be in equilibrium. And if it's in equilibrium, the forces have to add up to zero. Another way to see it is that the sum of the normal vector and the force of friction, so this right here, has to be the opposite vector of the force of gravity, which it is, because if you look at the resultant vector here, it's going upwards, whereas the force due to gravity is going downwards. So you can use either way of thinking of it. I like to think of it as the scenario or the box is in equilibrium with the forces because it is not moving. So I position all of my forces head to tail, and they must all line up nicely to give me that zero vector. So let's look at our final example. A box weighing 140 newtons is resting on a ramp that is inclined at an angle of 20 degrees. Resolve the weight into the rectangular components. So I'm going to draw my ramp to begin with. And it's 20 degrees. And there's a box on this ramp. Now, I of course have the force due to gravity, and we're given the force. It's 140 newtons. If we had been given the mass, then we would do the mass times 9.8, but they gave us the force right away. Then I'm going to have a force that is perpendicular to the ramp. So this force here, and it's acting upwards into the box. Now technically I could draw this force here as well, but I'm just putting it head to tail, so it's ready to go. And then I have the force of friction, which again, I can put it here, but I'm gonna shimmy it down so that all of my forces are head to tail. So here's the normal force, here's the force of friction, and there we are. Now, I have that nice 140 Newton force. I know that must be a 90-degree angle because one's perpendicular to the ramp and one is parallel to the ramp. And now I just need to get an angle in here. So I'm gonna start off by looking at this triangle. It's a right triangle. There's a little right angle in here, right there, which means this angle up here should be 180 minus 90 minus the 20. So that should be 70 degrees. And once I get there, now I can look at my triangle in blue here. I could use that angle if I want, or I can find this bottom one, and it is 20 degrees. I can use either angle. But now I'm just looking for the force of friction and the normal force using some SOHCAHTOA. So I'm going to use the 20 degrees, and the normal is adjacent to 20. So the magnitude of the normal force will just be 140 newtons, because that's the hypotenuse, times cos 20 degrees. I could have also just set up the SOHCAHTOA if I wanted to, and I get approximately 131.6 newtons. Then for the force of friction, I'm looking for the opposite side, so that's 140 times sine 20, and I get approximately 47.9 newtons. And those are our two forces, and I don't have to worry about the directions here because the normal is perpendicular to the ramp and the force of friction is parallel, which I will write in my therefore statement. Therefore, the normal force is 131.6 newtons perpendicular to the ramp, and the force of friction is 47.9 newtons parallel to the ramp. So whenever you have these objects on inclined surfaces, your rectangular components will not be horizontal and vertical, but they still do meet at a nice right angle, and we can use our knowledge in this case, because the box isn't moving, of equilibrium to set up our scenario.